Welcome to the Crystal Clear Electronics video series, where we are finishing our chapter on PWM with the third video.
Welcome to all our dear viewers. In the first two video episodes, we learned about the basic principle of pulse width modulation, or PWM. We saw how digital signals can be used to control analog devices. An important point to note is that some analog devices actually average the voltage that is switched up and down, such as a light bulb, a motor, or even an RC circuit, which we have looked at already. While for other devices, such as a flashing LED, it is not the device but actually human perception that averages. The light from the LED is actually blinking and not averaged, but we see the average brightness. By changing the PWM duty cycle, we can control the average value.
Now we are getting to know how timing works in our pre-installed circuit.
As a starting point, remember the astable circuit, which can be seen on the left side of the figure. In that circuit, we have seen that the capacitor C1 is charged through the resistors RA and RB, but it is only discharged through the resistor RB. The 555 IC outputs a high signal for TH time and a low signal for TL time, the marking H referring to the word high and the L referring to the word low. These can be calculated using the following equations. The duration of the high signal level TH is 0.693 times the sum of the resistances RA and RB times the capacitance of capacitor C1. The duration TL can be calculated using a similar relationship, 0.693 times RB times C1 capacitance. The total period time will therefore be the sum of TH and TL, which we calculate to be 0.693 times RA plus 2 times RB times C1. The frequency is the reciprocal of the period time, 1.44 divided by the sum of all the resistors, so RA plus 2 times RB, and the whole term in parentheses times the capacitance of capacitor C1.
Nice! I can see in the right figure that there is only one difference between the astable circuit and the PWM circuit. The RB resistance is replaced by a PB potentiometer and two diodes.
Yes, the difference highlighted to our viewers with green. The potentiometer PB can also be interpreted as two sets of resistors, that is PB1 and PB2, whose ratio can be set by adjusting the potentiometer, but their sum is constant. The diodes are required to separate the charge and discharge of the capacitor C1. Let's look at the figure, which will help you understand the functions of the diodes. So, the capacitor C1 is charged through the resistors RA and PB1, but is discharged through the resistor PB2. If we look at the on and off time formulas again, we can explain why our circuit implements the generation of the PWM signal. The duration of TH can be calculated as 0.693 times RA plus PB1 times C1. And the duration of TL can be calculated as 0.693 times PB2 times C1. Thus, the period time is the sum of TH and TL, which is 0.693 times RA plus PB1 plus PB2 in parentheses times the capacity value C1. That is 0.693 times RA plus PB in parentheses times C1. The frequency will be 1.44 divided by RA plus PB times C1. From this, we can see that the signal frequency will not change when adjusting potentiometer, since the values of RA and PB are also constant, that is PB equals PB1 plus PB2. Only the ratio of PB1 to PB2 will change, which will determine the duty cycle. The duty cycle, denoted by D, can therefore be calculated by dividing the period TH by the total period time. This is 1 minus the PB2 resistance divided by the sum of the RA and PB resistances.
The equations also show why we can't reach a duty cycle of 0% with this circuit.
As recommended by the datasheet of the 555 IC, RA should not be less than 1 kΩ because a too high current would flow through the IC. This would cause unnecessary heat or damage. So we turn the potentiometer in the direction of PB2 equals PB in vain because we will not have 0% duty cycle. You can also see on the figure that PB divided by RA plus PB can't be equal to 1. With this, we reach the end of the PWM topic. Hopefully, this chapter of the curriculum and the completion of the tasks helped you to better understand what exactly PWM is. In the next section, you will find even more exciting examples where the PWM will be produced with the help of a microcontroller. To make this video not only full of theoretical and computational steps, let's show a little of what this PWM controller can do. We pointed out in the previous video that there is a MOSFET here that allows you to switch to higher currents. And now, let's connect everything that's been connected to our system in the past. We see the LED flashing. I have now turned on the motor. It is not drawing very much current yet. However, when I connect this LED line to the system, with the current drawn, it's a pretty significant value, and we can see that our circuit will still work. So I'm gonna wire this one in now. I have to make sure that the polarity is correct. First, I connect the ground. Then I connect the positive polarity to the dotted 12-volt output. We can still see this blinking, but to make everything work properly, we know that by replacing the capacitor with a much smaller capacitor, we will get a very high frequency switched signal, so we see the light as continuous. And to demonstrate how PWM works, by turning the potentiometer, I can change both the brightness and the motor speed, as well as the brightness of this tiny LED. And I think this really shows the beauty of this PWM control.
I agree. Thank you Ambrus Zelei for his presentation, and thank you to our viewers who followed along with the 3 videos about PWM. You can download the curriculum in PDF format from crystalclearelectronics.eu or in Hungarian from kristaltisztaelektronika.hu. You can find a mobile app for Android and iOS platforms under the same name. You can always follow us on Facebook, and see you soon in the next videos. Bye bye.
Bye!